Alrighty. What's up, you guys? Welcome to Lecture 3 for Linear Algebra for Computer Science majors. In this section, we're going to be covering non-singular matrices and inverses of matrices. Now, I'm not really going to use this term, but your class might, so I'm just going to project this now. But it's really just it's just to relate with just trivial solutions and non-trivial solutions. So I'm not going to bother using the word non-singular since the majority of the times we're just going to be talking about homogeneous systems. Now, but to just in case if you do have in case if your class just wants to talk about non-singular matrices and brings this unnecessary word up so many times. So essentially what this means is a non-singular matrix is pretty much a square matrix where if you put it into a matrix equation, a homogeneous matrix equation, it will only give out as a trivial solution. So that's literally all that is, right? So if you put this matrix into a matrix equation and equal it to a zero vector, and it, if the only solution comes out as a trivial solution, then it's non-singular. That's all that means. But, I mean, genuinely, we're just going to use the term non-trivial and trivial solutions. But just in case if your class keeps using that word, it just means a matrix where you put it in a matrix equation and equal it to a zero vector. If the solution is only trivial, it's non-singular. If it has an infinite solution, then it's singular rather than non-singular. Okay? It's very redundant. I'm honestly kind of a little annoyed with this term, but just for those classes where they do use this term a lot, I'm just letting you know right now. Okay? Now, I'm going to delete that because we're not going to use that word here because it's really redundant. But I'm gonna label it as a title for the topic just because some classes use that word a lot. But essentially, or conceptually, if you remember, we have homogeneous equations. If you just to recall, right? Whenever we have a system, I don't know, cx plus dy, whatever system we have, and we have a bunch of zeros as our answer, all that is pretty much this is a homogeneous system, right? Just to recall, if our solutions is only zero, right? Let's say we're solving for x and y, and our only solutions are a zero vector, then it's a trivial solution, right? Because, it's trivial. Or I guess, to put it in a better perspective, whenever we have a system and we turn it into a matrix equation, like this, right? Turn a homogeneous system into a matrix equation, and we have our vector here. If this is our only solution where our vector, the stuff that we want to find, A, B, C, whatever, and our only solution is a zero vector, it's trivial, right? If not, then it is non-trivial and it has an infinite solution. And we have to actually find a specification for it. Okay? Just to recall. Other than that, you're good to go. You literally just learn just the background of how to deal with non-singular matrices. Okay. Now let's go ahead and get into some exercises related to this concept. Okay, so now we have an example here, right? So sometimes your class will be asking you, is this matrix A non-singular, right? In other words, what we're asking is, does this matrix, when we put it into the equation like that, into a homogeneous matrix equation, does it have a non-trivial solution? Or is it only have a trivial solution? So the way we solve for this, is we put it in a homogeneous system, meaning that our augmented matrix will look like this. So let me actually write this in yellow so that we don't get confused with the same matrix. So what this means is that we put it in a homogeneous system, right? And in other words, we put it in a matrix, an augmented matrix, where our answers, not our answers, the numbers is 0, right? Because in a homogeneous system, for each equation, it equals to 0. Okay? Now that we put that here, how do we determine if it has a non-trivial or a trivial solution? Easy. We compute the RREF. Okay? So we compute the RREF. So pretty much to determine if this square matrix is non-singular, or if it has a non-trivial solution when we put it in a homogeneous matrix equation, we pretty much turn it into a homogeneous system. So what we do is we grab the square matrix and put it in a homogeneous system, because every homogeneous system always has the numbers, the equations equal to 0, right? So that's what a homogeneous system, if you remember the homogeneous system, what that means. So of course we compute the RREF. I kind of lagged there accidentally. Technical difficulties. But just to continue, for the sake of time, when we compute the RREF, we end up having 1, 0, 0, pretty much the identity matrix on this side, while everything is 0, 0, 0. Okay? I'll go ahead and rewrite this too, just for convenience sake. Okay? Excuse my handwriting. But pretty much. So here, right, again, we put that matrix into a homogeneous system, and then we compute the RREF, and you can see that here it is completely isolated. This is an identity matrix, which means that there are no free variables. So that means that for some variable here, here, and here, they all equal to 0. And so because 0 is the only solution it has, that means that the 0 vector is the only solution that x is equal to. And I am lagging like crazy. But yes, so x is equal to the 0 vector, no other solutions. So that means that this matrix, that this does not have a non-trivial solution, it only has a trivial solution. And so therefore, that square matrix A, in your class, they would call it a non-singular matrix. That matrix A is non-singular because it only has a trivial solution. If it has free variables, then it would have non-trivial solutions. Okay? So that's how we determine if A is non-singular, or if a square matrix has a non-trivial solution when we put it in a homogeneous matrix equation. Okay, I know it's a lot. It's a lot to juggle, but the concepts, they connect. They kind of stack up a lot in linear algebra. Okay, but no worries, we're getting there. We'll get more comfortable with this concept, and we'll start to understand a lot more as we get used to it. So don't you worry. All right, let's go ahead and erase this. Okay, so now, how about this question here? So let's do this part. So if we put it in a matrix equation for any vector b, right, does it have a unique solution? Right? Does this matrix equation have a unique solution for any vector b? For any vector b, what that means, okay, let's see. So b can be any vector. So b can be literally any vector. Let's call this, I'll use x, y, z. Right. Or actually, I'll stick to a, b, c. I'll stick to a, b, c. Or, oh no, I can't do that either. I'll do RST. I really don't want to use x, y, z, because that could be like in here or be the solution for x. Okay, so how do we solve this problem? So again, when we're dealing with any vector b, this is how we generalize it. All right, so we'll generalize b could be any vector for some number rst. Okay, then you write it as an augmented matrix again. So now we go ahead, write your coefficient. This is technically our coefficient matrix, pretty much. Right, we're treating this as our coefficient matrix. And for any vector b, so it would be r s t. Okay? So now that we have our augmented matrix like this, now what we do is just like the usual, we compute the RREF. So we compute the RREF. Okay? Right? So our goal is to solve for x, right? X is like it's inside, the leading coefficients or what we want. So I mean, we've computed the REF before, right? The coefficient matrix actually does become the identity matrix, right? But here, now we have a solution. Now it's like it equals to something here. So looking at my notes, we see that we have r plus s plus t. Okay, r plus t. And then 2r plus s plus t. Okay? So this is what we have as our REF. Cool. So that means that our vector x is this. So this is what a vector x is now. Okay? So our x is equal to this, y is equal to this, and z is equal to this in terms of RST. So now that we have that, our answer, so I'll go ahead and put it down below here. X is equal to r plus s plus t, right? R plus t and 2r plus s plus t. Okay. Now, yes, we solve for x. So what this means is that yes, we do indeed have a unique solution. So, because, well, I mean, here, this kind of immediately shows that there's no free variables. So, because there are no free variables, then we do have a unique solution. If we do have free variables, then it's going to be a lot, well, just a little messier. I would say just a little messier. But it would not have a unique solution if we were to have free variables. But in this case, thankfully, we do not have free variables. So that is our x, and that is our only formation of x. Therefore, that matrix equation does have a unique solution for any vector b RST. So RST can be literally any number, right? And you just put it in that vector b, and your answer to the matrix equation will come out exactly in that format of vector x. Okay? So, if I plug in 1, 2, 3, so like if my vector b was equal to 1, 2, 3, then my vector x would equal like 6, 4, and 7. Yeah, 6, 4, and 7. That would be my answer for x. And x is only equal to that vector 6, 4, 7. Right? It's a unique solution. Okay? No free variables. So that's how we go about this type of problem. All right? All right. So now that we covered, the concept of non-singular matrices, or the concept of a square matrix that has trivial solutions only when we plug it into a homogeneous system, right? Now let's get into a different concept. And with that concept, we're going to learn about how inverse matrices work, right? So, now, yes, some matrices, we can have an inverse. And what I mean by that is they literally can have an inverse. Right? If we have a matrix A, there are matrices where they have a complete inverse. Kind of like functions, where there's an inverse function, exactly like how matrices can have too. So we can have an inverse matrix. Now, however, not all matrices has inverses, right? So we do have another concept as what we call it invertibility. So pretty much a matrix, or a square matrix, mainly a square matrix, it's not very well. The truth is, a rectangular matrix can't exactly have a inverse, right? So I mean, that's one of the the clearest example is that a rectangular matrix cannot have an inverse, right? And that's because of matrix multiplication. Because of matrix multiplication, there are certain matrices that you cannot multiply together. Okay, because if you remember from our previous course, our previous lecture, you can't always multiply two matrices depending on their size. Okay, so because of that, rectangular matrices don't really have a inverse. So when we say an inverse matrix, we are mainly talking about a square matrix. Okay, but that doesn't always mean that every square matrix has an inverse. That's not, just be very careful with that. Not every square matrix has an inverse, but mainly matrices that do have inverses are mainly square matrices. Okay, so let me go ahead and we call this concept invertibility. What does it mean for a matrix to be invertible? So I mean, all it means is, it just means like, if a matrix has an inverse, then it's invertible. That's literally all that means. Okay, nothing really special. If it has an inverse, it is invertible. But how do we know if a matrix has an inverse? That's what we're going to go over. But for now, I just want to get you comfortable with vocabulary terms. My question to you is, let me put it this way. Is B an inverse of A? Is B an inverse of A? How do we check that? Here's how we check this. If we multiply A times B, and it equals to our identity matrix, then B is equal to the inverse of A. Okay? So this is like the beginning how you would test matrices for inverses, right? If you multiply both of them and they equal to the identity matrix, then B is an inverse of A. Okay? So if you compute this, you could just compute it in your calculator, honestly, or program it. That would be a very nice practice. Okay? So when you actually compute this in a calculator, it actually does equal to 1001. Is this an identity matrix? Yes, it is. If you remember, this is an identity matrix. So, because when multiplying two of those matrices together, they do equal to the identity matrix. So what that means is that B is the inverse of A. Okay? So B is definitely the inverse of A, since AB is equal to I. And because this is equal to I, what this also means is that BA, this means if you have invertible matrices, then AB is equal to BA. This is only true for inverses. This is only true for inverses. Oh, I wrote it right here. There we go. Okay? For invertible matrices. All right. Cool. So that's all that means. That's all it really is to it. It's just invertibility. When they say is the matrix invertible, they're just asking you if the matrix has an inverse. And if it doesn't have an inverse, then it's not invertible. Okay? Not every square matrix is invertible. Not every square matrix has an inverse. Okay? Like a good example is a zero matrix. Right? Consider a zero matrix. Let me go ahead and delete the whole board. Okay? This is a very easier example to show you. If you remember a zero matrix where it's all a bunch of zeros, okay? This matrix does not have an inverse. So, because of that, it's not invertible. Right? So not every square matrix is invertible. Just want to point that out. Okay? So now we have another square matrix, A. Okay? Now, it's, the same question. If we put this in a homogeneous matrix equation, does it have a non-trivial solution? Right? So, if I put this in a homogeneous matrix equation, does it have a non-trivial solution? Is this matrix A non-singular? So, what that means is we're going to go ahead and turn it into an augmented matrix, right? We go ahead, put an augmented matrix. Right? And now what we do is we compute it. We compute the RREF of it. Now, when we compute the RREF, it does not turn out to be like an identity matrix. It actually turns out to be something a little ugly, but just, it's okay. Just don't freak out. It turns out to have free variables now. Oh no. So now we have free variables. We have free variables, and we have a free variable here, right? So what this means is that we do have non-trivial solutions. And the reason is because now we have, I'll go ahead and write it here. We now have x equals to, let's say, this is like x, y, z, let's say, right? Now we have like negative 1/2 of z. And then y has negative 1/2 of z. And then z is our free variable here, right? Because we can't solve for z. So now we have a free variable here. And so now what this means is that x is literally any form. I should probably I should have changed it. Actually, now I think about it. Let me change the variables. I'll turn it back to RST. Let's say that. RST, right? And t is our free variable. Okay? Right. Then our vector x that we are solving for is no longer a unique solution. Now we can have literally any t pretty much, because t is our free variable. Plug in any number t and it's just literally anything. So what this means is that this x does not equal to 0, 0, 0 anymore. Now this x actually has some numbers in it where, I mean, yeah, you can let t equal 0, then it'll be our trivial solution, right? But if I let t equals to 1, now it's not a trivial solution anymore. Now we have other numbers, right? And we could let t be literally any number, and it would satisfy that matrix equation, the homogeneous matrix equation. So what this means is that this matrix is not non-singular, it is singular, and that this matrix equation does have a non-trivial solution. It does have a non-trivial solution. In which case we have to specify the formatting of the vector of our solution. In this case, it looks like this. It is formatted like that. Now that we know how inverses work, right? What is an inverse matrix? What does it mean when people say it is a square matrix invertible, right? So how does it work? In a computer science question, how does inverse matrices work? How are inverses of matrix programmed and computed? So let me show you how matrices are, here's how we find inverses of matrices. Okay? So let's say that we have a square matrix A, right? I'm just going to write it right here. Let's just say that we have a square matrix A. Okay? And we want to find the inverse of this square matrix A. Okay? So how we program this to find the inverse of A forcefully is we turn it into a very huge augmented matrix, right? Usually when we write an augmented matrix, the right side, right, when we go like that, oops, that does not look good on your camera view. There you go. Usually we only have one slot, right? However, when we program and compute the inverse, we're going to have more than one slots. In fact, we're going to have another square matrix here. And we let this side equal to I. Okay? So what we do is we form it in an augmented matrix where the left side is the matrix that you want to find the inverse for, and the other side is the identity matrix. Okay? Now, why are we using identity matrix? You'll understand why later. So what we're gonna do is we're gonna perform an RREF. We're gonna perform the RREF onto this huge augmented matrix. And what's gonna happen is we end up. So pretty much what we want to do is we're gonna turn this A into I. Now, you understand how RREF works, right? Sometimes when we compute the RREF, it doesn't turn into I. Then what that means is that square matrix that you're trying to find the inverse for, if it does not turn out into an identity matrix, it means that it's not invertible. It means that there is no inverse, right? If this side looks like it has free variables, then whatever square matrix that you're trying to find the inverse for, it doesn't have an inverse. It does not have an inverse. It's not invertible if it does not turn out as an identity matrix. Now, but let's say majority of the times it does. Then on the other side, you get another matrix, B. This is your inverse, okay? And that's it. That's literally how we compute for the inverse of any square matrix. So if you want to program, like an inverse matrix calculator, and you want to program it, this is how it works. Okay. In fact, let me go ahead and just kind of demonstrate. Just do a short demonstration. I'm not going to use the Gaussian Jordan elimination like before, because dear God, that was terrible. That took up like half of my lecture. So let's do an example, right? So what does it look like when we want to program our, let's say, we just want to program, oh God, I am lagging. So let's say we want to program a inverse matrix calculator. Okay, this is the mechanism behind that program, that calculator. So let's say we want to find the inverse of this square matrix. Okay, this 3x3 matrix, and we want to find the inverse of this. Okay, so how do we compute the inverse of this big 3x3 square matrix? What we do, how computers compute the inverse, here's how the program works. What we do is we turn it into a big, gigantic, double augmented matrix. So we put A here, right? We'll go ahead and put 3, 1, 2, 4, 5, and -1, 3, -4. Okay. So, I'm sorry. We don't end it with square brackets. I'm sorry. This is a double augmented matrix. So what we do is we put an augmented line here, and then we write the identity matrix. Okay. All right. This is what I mean by like a gigantic double augmented matrix, right? So we put it in this form. So the computer, or in the program, it forms it like this into a gigantic matrix. And then what we do is, now that it's a 3x6 matrix, we compute the RREF. We compute the RREF, and what it does is it'll now turn this into an identity matrix and then have this something else, in which case this side will become the inverse. So now we have, when you compute the REF, it will turn out like this. Right? This will give us, oh God, it gives us an ugly number. 3 halves. This gives us 3 halves, -1, -1/2. Oh God, it's giving us ugly numbers. Oh God, very ugly numbers. -11/10. We have 1, 7, 7/10. I have 1 here. 2/5. -6/5. Okay, a little nasty, but that's okay. Sometimes we do end up with nastier inverses, right? We have a very clean square matrix, and sometimes the inverse of the square matrix can end up looking nasty, right? So the inverse of its matrix can be nastier. So, but yes, that is our inverse. So this square matrix here is the inverse of A. Okay? Like I said, if this side does not end up looking like an identity matrix, then what that means is that the square matrix that you're looking for, the inverse of the square matrix that you're looking for, does not have an inverse. Okay? That's all that means. If it does not turn out like this, it does not have an inverse. That square matrix that you're computing with, it is not invertible. That's all that means. Okay? Cool. So that's what it looks like. That's just how the computer computes inverses for, for square matrices. All right? Cool. So that's the mechanism. It's actually pretty simple. Cool. All right. Time for the bonus part. Let me give you just a little bit cheat sheet. I think you're not supposed to learn this when you're learning invertibility for the first time, but it's okay. I'll let you off the hook. You guys are only computer science majors, so it's no worries. It's no worries. So, whenever you have a 2x2 matrix, right? For any 2x2 matrix, A, B, C, D, okay, just for a 2x2 matrix. I'm not going to give you a formula for like bigger ones. We're going to deal with those harder concepts in the next lecture. But for now, a 2x2 matrix, if you have for any 2x2 matrix, the inverse of this is equal to AD minus BC. This is a fraction, yes. This is an actual number. It's a scalar multiplying a matrix in the form D negative B negative C and A. Okay? This is the formula for the inverse of any 2x2 matrix. Now, like I said, right? Not every square matrix has an inverse. And here's how we can easily tell. It's because of this. Okay? This is what determines if a square matrix is invertible, right? So if, just to recall, in math general, you cannot divide a number by 0, right? If this is equal to 0, you're screwed. Well, not exactly. All that means is that if this whole thing is equal to 0, the inverse does not exist. That square matrix that you're dealing with is not invertible. It does not have an inverse. So whenever this is equal to 0, it does not have an inverse. If it does not equal to 0 and it actually equals to an actual number, then congrats, you have an inverse, right? There you go. You have an inverse. So a quick way to determine. So this is technically another definition of invertibility. So there you go. Congratulations. We have our second definition that your class might go through. Okay. This is our easiest definition. Okay. If it does not equal to 0, if this does not equal to 0, then it's invertible. It has an inverse. Okay. If it does equal to 0, it's undefined. You cannot divide a number by 0. So, because of that, the inverse does not exist. That square matrix is not invertible. Okay? Cool. There you go. Don't tell your professor I showed you this early. Okay? Cool. Now you know the secret, how to compute a 2x2 matrix by hand. Or a quicker way to compute an inverse 2x2 matrix. Create a program as like a calculator, and you could just use that formula. There you go. Bam. You don't have to use the double augmented matrix program code or whatever, the mechanism process, right? Just use this formula and you're good to go. There you go. Works for 2x2 matrices, right? But if you're looking for an inverse for a bigger matrices, then you're just going to have to use that double augmented method. Okay? Cool. Alright, the last thing I want to do in this lecture is to show you the inverse properties. So now we have inverse properties. So, yes, we do have some algebraic properties with invertible matrices. Okay? So let's go ahead and get started with those invertible matrix properties. So the first one is the easiest, right? The inverse, if you want to compute the inverse of the inverse of A, it's just simply going to equal to A. Okay? So that inverse, the inverse here is just going to cancel out. So the inverse of A is equal to A. That's it. Very simple. All right, number 2. Property number 2 is whenever you have A and B, okay, the inverse, right, make sure that these two matrices are invertible. The inverse of the multiplication of A and B is specifically equal to the inverse of B times the inverse of A. It is not the other way around. It is specifically B first, then the inverse of A. Okay? Because again, remember that in matrices multiplication, this is not always true. Not always true. Not in matrices, unfortunately. So, because of that, the inverse of the multiplication matrices AB is equal to inverse of B times inverse of A. Okay? So just keep that in mind. Okay? Specifically this format. Alright. Number 3. What about the inverse of a scalar for some number like k times a matrix A? What is the inverse of this? The inverse of this is equal to 1 over k of the inverse A. Okay? And k is literally any real value. And obviously for every scalar we use, right? For every scalar we never have a scalar that's 0. Right? That's just stupid. Why would you multiply 0 to a matrices? That'll just make everything 0. So, of course, scalars, we never use a scalar that equals to 0. So, again, for a scalar k, the inverse of ka is 1 over k times the inverse of a. Okay? Alright. Last property, number 4. Okay? Number 4, and that is whenever we have an inverse of A, our last property is if you want to find the inverse of the transpose of A, okay, then this is the same thing as transposing an inverse of A. Okay, so I just want to make sure the inverse of a transpose matrix is the same thing as transposing the inverse of that matrix. Okay? And there you go. These are your 4 main popular properties for inverse matrices. In fact, I'll actually add this in. Let me add this in. I'll color this in blue. Okay? So we can also have a negative exponent like this. And let's say, you have a matrix and it's like to the power of negative p. Then what that means is that we are multiplying the inverse of A, the inverse of A, the inverse of A. We are multiplying the inverse matrices p times. Okay? Or I guess you can put it, we are computing the inverse of the A, to the power of p. Okay? So, not gonna lie, this does bug me. So I'll mainly just use this notation. Okay? But yes, sometimes you'll see some books that writes like this. It's the same thing as this. Okay? Right? You cannot have like 1 over a matrix. No, no. This is referring to this. Okay? All right. And I believe that is it for this lecture. So that's it. It's just non-singular matrices and then inverse matrices. Okay? All right. Cool. Again, just a reminder, we do have problem sets. It's going to be in the description, and practice, and you'll definitely be more comfortable in linear algebra. All right. So I hope that was helpful, and that covers a lot with some confusing vocabulary words. But other than that, thank you guys so much for watching, and I'll see you guys in the next lecture. See ya.